Hello, my name is Yang Wei. I'm from Jiangxi Normal University, Nanchang, China. I'm very pleased to be here to join this forum. The topic of my presentation is a decentralized scheduling algorithm for TSCH-based wireless networks. My presentation will include 4 parts. First, I will give an introduction of the paper. Second, I will propose a decentralized scheduling algorithm for TSCH-based wireless network. Third, I will introduce the simulation setup and show our experimental results. Finally, I will conclude the paper and present our future work. First, introduction. Industrial wireless sensor networks will be widely used in the field of industrial process automation in the future. The technology can greatly improve the efficiency and the quality of industrial production. Industrial automation applications have stricter requirements for low power consumption, high reliability, and real-time performance of wireless network. These demands have been difficult to fulfill until the introduction of the time-slotted channel hopping (TSCH) technology. All nodes in a TSCH network must maintain high presentation synchronization. The nodes radios switch on according to the network schedule, which can avoid idle lessons. It also uses a channel hopping technology to improve the wireless communication reliability. Figure 1 shows an example of communication in TSCH-based wireless networks. There are 5 nodes in the wireless networks. Each node should keep a high presentation synchronization, and they can use the different channel to communication. The communication of nodes happens at a slot offset channel offset location according to the network schedule. However, it doesn't define the function how to address or delete relocated cells between neighbors. The exacting schedule algorithms in TSCH-based wireless networks can be classified into 2 categories: central scheduling and distributed scheduling. Centralized scheduling algorithms are only suitable for static networks. So, most exacting scheduling algorithms for TSCH networks involved distributed scheduling. In our paper, we will propose a decentralized scheduling function for TSCH-based wireless networks. Our schema will consider the user probability and the distance of there, rather than simple random selection. We implement a decentralized scheduling function in a TSCH simulator, and evaluate its performance experimentally in different cases. The experimentary results show that our purpose scheduler can reach lower end-to-end latency, as well as no extra contrast. Second, we will propose a decentralization scheduling function. According to the latest TSCH minimal scheduling function document, it specifies when to add or delete time slots, such as adapting to traffic, switching parents, and handling schedule conclusions. But it didn't define how to select time slots. Time slot selection is very important in the resource scheduling algorithm, and it will directly affect the end-to-end delay and the reliability of the network. Our schema is to minimize the end-to-end packet transactions delay. It selects a suitable cell from the available cell list based on the user probability and distance of the cells. Table 1 shows the system symbols in the decentralized scheduling function, such as list TX is the available TX cell. List RX is available RX cell. PTI is the packet transaction proper of the ITX cell. PRI, DRI, and slot names, and so on, system symbols. The core idea of our schema is to select a most suitable TX cell from list TX, which can make the sum of the distance to all RX cells the shortest, thereby ensure the noticed time delay. Each TX cell and RX cell has an ASM value. The distance between the TX cell and the RX cell can be calculated by the equation 1. If TX ASM bigger than RX ASM, we can use this equation, and If it's lowest, we can use this. Assuming the number of available x there in the list x is k, we can calculate the sum of distance from the one selected dx there to all x there based on the equation 2. And PR1 at PR2 at PRK is 1. Assuming the selected tx there is times not 14, we can calculate the distance dr1 is 10, 14, 4 is 10, dr2 is 5, and dr3 is 21 based on the equation 1. Further, assuming the proper PR1 is 1.3, and PR2 is 1.6, and PR3 is 1.1, 0.1. We can calculate the sum of distance is 8.1 based on the equation 2. Using the same method, we can calculate the sum of distance value under different tx there. If the selected tx there is time slot 8, the sum of distance value is 15.9. And if the selected tx there is time slot 18, the sum of distance value is 9.8. By comparison, we can infer that the shortest distance can be achieved by selecting dx time slot 14. Node B has 3 x stairs from node A, time slot 4, 9, and 16, and 4 tx stairs to node R. To each tx stair, node B counts the number of sending packets. Here, the tx stair with the noticed packet transaction property need to be deleted. In figure 3, the tx stair time slot 11 need to be removed. Third, we will introduction the simulation setup and show our experiment results. We adopt TSCH open source simulation to evaluate our decentralized scheduling function. The 6th TSCH simulation is a decentralized event simulator written in Python, which is fully supported TSCH protocol stack. Table 2 shows the experiment parameters. The experiment results. Here we may consider two metrics, avoided end-to-end latency and mark reason end-to-end latency. Figure 4 shows the avoided and maximum end-to-end latency of SF link. LLSF and all-purpose function in different cases. As shown in Figure 4a, the avoided end-to-end delay of all-purpose schedule is much lower than that of SF-link and ASF in different traffic rate. When the traffic rate is 1 packet minute, the avoided end-to-end delay of all-purpose schedule is only about 0.75. At the same time, the avoided end-to-end delay of SF-link and ASF reached 2.89 and 1.81. Compared to SF-link and ASF, the avoided end-to-end delay of all-purpose schedule has dropped significantly. Figure 4b shows the reasons end-to-end latency of our purpose schedule is much lower than SF-link and LLSF. Finally, I will conclude the paper and present our future work. We may present an infection decentralized scheduling function for TSCH-based wireless networks. First, we present a cell selection method which fully considers the user purpose and the distance of cell. Second, we propose a cell detection deletion method which fully considers packet transaction proper. It can reduce network energy and consumption. Finally, we implement of our purpose schedule and verify its performance through experimentation on the 6TI-SCH simulator. In our future work, we will deploy our purpose schedule in a real-world 6TI-SCH wireless networks to further verify its performance. That's all. Thanks very much.